This is what we started in the last class, sinusoidal steady state analysis. Questions about this so far, please? I know for a fact that there are some areas that are not 100% clear yet. And the only way that they'll become absolutely clear is practice, practice, practice. And we are going to go over a bunch of problems today. But this is one of those chapters where you have to fake it till you make it. So until then, you just have to, even the textbook delicately hints that there are some gaps, okay, that we just have to leap through and accept the results. And then when we practice a whole lot, that's when it's going to make intuitive sense. Okay, so let's see, let me point out to you the specific location, okay, where the textbook kind of hints that there's a bit of a gap. Right here, we largely ask that you accept this representation and move quickly to the way we can now express past. So the idea being, it's best if we try to get intuition through practice rather than trying to brute force understand this. Okay, it's not really complicated. It's just easy to get lost in the corners of numbers. Okay, so besides that, other questions, please. If you still have questions, I would like to know what specific questions you have. That way I get a sense of what is a muddy point in your understanding so far. If there are specific points that are not clear to you or that you'd like for me to go over, again, I'd be glad to. It's very important for me to know what those areas are.
You haven't gone over it yet, but I'm interested in knowing how the term E is equivalent to the cosine plus sine. Yes. So that's what is the muddy point for me.
Yes. This is a really, really interesting relationship, Euler equation. The proof of this is beyond the scope of this class, but this really ties so many different concepts together into one equation. Okay, and I'm not sure I'll be able to go over this in the class, but the idea is E, the term that represents exponential growth in the universe, that's in nature. Okay, if you take something, any quantity, double it, and then double it again, and then double it again, all of that kind of growth, okay, that kind of exponential growth is represented by the quantity E. Okay, that is tied to the trigonometric relationship between cosine and imaginary part sine. And that's a very, very interesting, a fundamental equation that we will use over and over again in this class. And the proof of that is a little beyond the scope of this course. Other questions, please? As a matter of fact, I tell you what, there is a very interesting video on YouTube that I encourage you to look up. I think it's the number file guys who talk about this in a much more excited and very interesting manner. Let me point you to a very interesting video on YouTube by number 5 fellows from, I think, a couple of English folks. They make interesting videos, and then I encourage you to look that up when you have time. Other questions, please? That's a good question, because that is that underpins a lot of our discussion today. E to the j theta is cos theta plus, this is plus or minus j sine theta. Okay, a complex number with a real part and an imaginary part is equivalent to the exponent e to the j theta. Okay, there's a real part, there's an imaginary part. Other questions, please? Okay, let's quickly review what we did in the last class. And because we went over a whole lot of material, this is what I'm going to do. I'm quickly going to walk through each of the slides, and then eventually, let's see, let me bookmark this page. Eventually, as we walk through each of the slides, I'm going to write a quick summary of what we did so far. Okay, let's see. Let's begin there. Okay, steady state. This is what we started off doing: sinusoidal steady state analysis. Right, sinusoidal steady state analysis, where we talk about time varying voltages and current. And I mentioned that we'll be using a phasor method. Okay, complex numbers, and phasors to make our calculation very, very easy. Okay, or reasonably easy. That's what we started talking about in the last class. Okay, and then I talked about the polar form and the rectangular form. Okay, I want to come back to this later. We'll talk about polar form and rectangular form and how to convert from one form to another form. Okay, how to go from polar. Let me see if I can write it in this color. Okay, from polar to rectangular, back and forth. Okay, and I'll show you a very clear-cut, concise method to do that using numbers. Okay, we could do that using this real part and imaginary part. Okay, but I'd like to reiterate that. I'd like to emphasize that. Okay, using numbers. That way it's much easier to remember. Okay, so we'll come back to that. So here is what we started doing. Okay, the idea of a sinusoid. Okay, the idea of a sinusoidal wave, um, where we use cosine. Okay, V is, or let me be more clear, V of t is Vm cos omega t plus phi. Okay, so this is a representative time varying cosine wave for your voltage. If I had a time varying current, I would write it as Im cosine omega t plus phi I. Okay, to represent that it's a phase that corresponds to the current. Okay, time varying signals. Let's go back. Okay, let's go back there and see. This is the, and then of course there is a frequency component to it, and there's a angular frequency component to it, and there's a phase to it. And we talked about the relevance, significance, and the intuition behind this extensively in the last class. Okay, and then we know how to go back and forth between angular frequency and frequency in degrees. Okay, now, and then we know the time domain representation and how to derive the phase angle. How do you get the phase if some information about the value of the wave at time t equals to 0 is given? Okay, if the value at time t equals to 0 is given, how do you find the phase? That's something that we have discussed in the last class. Okay, then let's see. So this is all about sinusoidal wave. Then we went on to talking about the Vrms value of a sinusoid. Okay, the Vrms value of a sinusoid is Vm over square root of 2. So if I had a wave like this, V of t, what is the V RMS value of this guy? Okay, the V root mean squared value of that guy is simply the peak voltage over square root of 2. Okay, that's with no DC voltage. If there was a DC voltage, so if you had a wave that had plus V DC about it, then Vrms would be, so let me do this, style this to incorporate a yellow color there. So Vrms for a wave if the DC value is included, then it will be VDC squared plus Vm squared over 2 the whole root. Okay, so much we know. So this is one of the things that we discussed in the last class. How do you find the Vrms for a sine wave? Both of these equations are valid only when your signal is sine wave, or more generally, sinusoid waves. Okay, with some DC component. Now, let's go back. Okay, let's see. So that's the sinusoid wave and sinusoid wave with DC component. How do you find the RMS value? Okay, that's something we discussed in the last class. Okay, then we went on to talking about the sinusoid response. And then I kind of discussed about the idea of linear and non-linear circuits. Okay, linear and non-linear circuits. I know this concept may not have been explained in a 100% clear manner, but that's something I want you to ask me if you have questions about. I just don't want to go on a wild goose chase, spending more and more time on it. If you do have question about it, you're welcome to come back and ask me in the class or outside the class, if for some reason that part is not 100% clear. Then I mentioned that the sinusoidal response, when you apply a sinusoidal input to any circuit, its response has two components. Its response has a transient component and it has a steady state component. And I mentioned that in this class, okay, in this chapter, we'll be talking about steady state response. Okay, so let me see if I can record that as well. Okay, let's see if I can go back here. Okay, we are summarizing all the concepts that we discussed so far. There's a sine wave, the RMS value, and then the idea is that the overall response of a system, overall, is equals to the transient response plus a steady state. Steady state response is similar to the long-term response. I gave you an example as to how you can relate it to a journey in a flight. When you're taking off, the initial acceleration that you experience is transient, and the steady state, more settled response that you experience when you're going on a long flight, the constant velocity or the acceleration, that's the steady state response. Okay, so there are two things, and the subject of this class and this chapter is steady state response. Okay, that's what we discussed. Let's see what else. Okay, and I mentioned there are different properties for the linear circuit. Okay, the steady state response of a linear circuit, if the input is sinusoid, the output is also sinusoid. One thing, the frequency of the circuit's response is equals to the frequency of the input. So the frequency does not change when you pass it through a linear circuit. Okay, the amplitude will change, may change, most probably than not, and the phase most probably most probably than not will change. Okay, so when I have a circuit, or when I have any simple circuit, let's see. and I apply a sinusoid input, the output is also going to be a sinusoid, okay, with the same frequency, but different amplitude, different phase. Okay, so here is what I'm going to, here is how I'm going to show that. Let's see. Okay, let's go back here. So the output, let me write it like so, output of a linear circuit with amplitude A1, phase phi, let's call them I for input, okay, and frequency input. If these are your inputs, okay, to a linear circuit, the output is going to be a function of amplitude O. So there's going to be a different amplitude. The phase is going to be different, but the frequency of the output is still going to be the same. Okay, so that's my way of representing that what changes between input and output is the amplitude, okay, and the frequency. I'm sorry, and the phase, but not the frequency. Okay, so let's see. That's one of the summary points I want to highlight. Now let's go back and see what else we can do. Okay, and then we started talking about the phasor. Okay, the phasor, which is fundamentally based on the idea that e to the j theta is cos theta plus j sine theta. I'm going to come back to using this over and over again, a e to the plus or minus j theta. So let me write that again. So here, a e to the plus or minus j theta is a cosine theta plus or minus j a sine theta. Okay, let me see if I can show this better. Okay, with a bit more boldface. Okay, let me see. Okay, so let's see. So that's what we discussed, one of the things we discussed in the last class. So let's continue our review on this page as well. Okay, so review of what we did in the last class. Okay, all the important things that I want you to get, just so we can proceed with the problems. Okay, now one of the things I did not spend a whole lot of time talking about is that this guy Vm e to the j theta is the phasor transform of Vm cos omega t plus phi. Okay, so let me write that down. Okay, so let's see. If I have a cosine wave, okay, if I have a cosine wave, Vm cosine omega t plus phi. The phasor transform of this, okay, the phasor transform of this is Vm e to the j phi. Okay, this is the phasor. Okay, so in other words, all I'm doing is I'm looking at the amplitude and I'm looking at the phase angle. Okay, when you collect the amplitude and the phase, that representation is called the phasor transform of the cosine wave. Okay, that's the phasor transform of the cosine wave. Let's go back. That's the phasor transform of the cosine wave. Okay. Now, So we're going to come back to this because it's very convenient to express our sinusoids in phasor form, because it's much easier to do a lot of arithmetic there. Okay, and then I showed you the kind of relationship. I showed you the relationship. So one proof here, okay, one proof here is that the A cos phi plus A sine phi, the whole square, is equals to the A squared. Okay, Pythagoras theorem says that the sum of the uh, two sides of a right angle triangle equals to the square of the hypotenuse. Okay, let's see. Now, I discussed, I kind of showed you how if you represent a complex number on the x and y axis, okay, with the x-axis carrying the real part and the y-axis carrying the imaginary part, I mentioned that you can represent a point in this Cartesian coordinate using its x and y coordinates, or using a magnitude and angle. And that's kind of the intuition behind conversion between polar and rectangular form. Okay, that's what I discussed. Let's see if I can go back to doing that. So if I have a number, okay, that's like x plus, if I have a complex number, x plus jy, and you want to translate that into polar form, where it is represented by magnitude and phase, then the magnitude is given by the hypotenuse, which is x squared plus y squared. Okay, and phi, and I didn't mention this in the last class, the phi phase angle is given by the imaginary part over the real part. Okay, the tan inverse, the arc tan of imaginary part over the real part. That is how you would go, you would calculate, if you wanted to calculate the magnitude, okay, of the polar form from the x and y coordinates. So going from rectangular to polar form conversion. Okay, if you wanted to go the other way, if you had a and phi and you wanted to calculate x, x would be a cosine phi, y would be a sine phi. Okay, so this is interconversion. How would you convert between rectangular form to polar form? And these parts are easy to see. Okay, the angle, if you think about it, the angle phi, the adjacent part is x, okay, along the x-axis, okay. The imaginary part is y. Therefore, tan inverse of opposite side to theta by adjacent side to phi, I'm sorry, the opposite side by adjacent phi would give you the tan angle. Okay, so it's easy to see how they're related, okay, in terms of the, and of course, this guy is the magnitude, which is x squared plus y squared, and that's exactly what I have here. Okay, real part squared plus imaginary part squared. Okay, so if you can go back and forth with the diagram here, it's easy to convert rectangular to polar back and forth. Okay, let's see. Let's go back there. Okay, going back and forth between rectangular and polar forms. Okay, what else? What else did we do? We went on to talking about the passive circuit elements in frequency domain. Okay, passive circuit elements in frequency domain. Let's see if I can summarize that. Okay, passive circuit elements in frequency domain. A resistor in time domain is governed by the equation V equals to I times resistor. In the frequency domain, okay, in the frequency domain, let's see. In the frequency domain, the equation for a resistance is still VR. Voltage across a resistance is IR times R. Okay, so nothing really changed. Let's look at inductor in frequency domain. V of an inductor is L di by dt. That was the governing equation in time domain. Let me see if I can park this somewhere there. So I'm going to write this as time domain. Versus this guy to be frequency domain. Okay, in frequency domain, the good thing was that the governing equation for inductance was converted to a form that is similar to the Ohm's law. Okay, in frequency domain. Okay, V is IL times ZL, the same with C as well, the capacitance. I of a capacitance was C dV by dt. In the frequency domain, the capacitance can also be expressed in terms of C, ZC. Okay, but you may ask me what ZC is. What is ZC or ZL? ZL, I showed it to be J omega L. It's the complex impedance. Okay, it's the impedance ZL and ZC are called as impedances. ZC was 1 over J omega C. Okay, and we are going to look at some problems that involve. Okay, this is called impedance. Okay, this is similar in sense to the resistance, the property of a material that impedes current flow, that stops free flow of current. Okay, so ZC is 1 over J omega C, ZL is J omega L, where ZL and ZC are called impedance. Okay, and I'm going to do some problem and introduce some interesting terms. Let's go back. Okay, let's go back here. What else did we do? So we started looking at passive circuit elements in the frequency domain. Okay, passive circuit elements in the frequency domain, and I kind of glazed through. Okay, and I kind of glazed through this this process here, the equations that we followed in terms of translating. Okay, inductor from time domain into frequency domain. Okay, and then we're going to look at some example problems that clarifies all of this today. Okay, questions please, questions so far. So that's a pretty long review of what we did in the last class, in the hope that I have captured only the important relations that we will be needing moving forward. Okay, questions please, questions so far. Okay, so let's see if we can continue with some examples here, and then a lot of concepts are going to become simpler when we look at some example problems. So let's start with this problem. Rather than solving it on this PowerPoint slide, I'd like to draw this from ground up. Okay, that way it's easier to see how it is built. So the question is, given this circuit, okay, given this circuit with a resistor, okay, there is a resistance, there's a another branch with a resistor and an inductor. Okay, and then of course there's a capacitance. Okay, there's a capacitance over there. So this is example. So there are many parts to this question. Okay, example problem number 1. Okay, the first problem, the question is, given this guy, the current of this current source IS is given to be, dang it, IS is given to be 8 cosine 2 into 10 to the 5 t amperes. Okay, the current is given for this guy. The value of the resistances are given 10 ohms, 6 ohms, 40 microhenry, okay, and then 1 microfarad. Okay, and then let's see what else is given. These currents are labeled as I1. The current here is labeled as I2. The current here is labeled as I3. The current in that branch. Okay, so that's the same current flowing here. Okay, so the question, there are a bunch of parts to this question. The first thing is find the construct. So question 1, part 1 is frequency domain equivalent. We are supposed to construct the frequency domain equivalent of this circuit in time domain. It's given to be in time domain. Okay, so let's see how we can do that. Okay, so let's begin by doing the solution here. Okay, so the first question is, given a circuit with a resistance, inductance, and capacitance, a bunch of different times, and a time varying input signal, how do you construct the frequency domain equivalent of it? The first thing I'm going to do is take this current source IS and represent it using its phasor. Okay, see, when I convert this time domain signal into phasor form, I'm using boldface capital letters. Okay, the phasor equivalent of this guy is, remember, 8 angle 0 degrees. Okay, let's go back to the let's go back to the summary here and see how we can represent the phasor equivalent. Okay, the phasor equivalent, if you remember right here, was Vm, the peak value is taken, and the phase angle is represented. So the phasor transform, the first thing we do is to do a phasor transform. When we do a phasor transform, we are just taking the amplitude value and the angle value. Okay, so that's what I'm doing here as well. So when I have to write the phasor transform of this current source, when I write the phasor transform of this current source, I'm just looking at the amplitude, which is 8, and then the phase angle, which is 0. Okay, so that's the current source in phasor form. Okay, so this is the phasor form of the current source. So the next thing I'm going to do is to transform the inductor. Okay, look at the inductor and then find out the impedance, the complex impedance of this guy. Okay, so now complex impedance of this guy, ZL for an inductor, was given to be J omega L. All right, if you remember, go back. So for an inductor, for a resistance, V is IR. For an inductor, I times J omega L. For a capacitance, I over J omega C. Okay, that was the inductance, capacitive inductance. Capacitive impedance, sorry, capacitive impedance. So for an inductor, The inductive impedance is j omega L. So that is what I'm interested in finding out. So what would that value be? J times, what is omega here? Do I know the value for omega?
It's 20 micro radians per second.
That's the value of L. The value of L is, wait, hold on. I think you, 22 into 10 to the 5 radians, correct. So that's the value of omega, right? Because that's given to be omega here. Remember the cosine Vm cosine omega t plus phi. So that part is the omega component. That part is the omega component. Okay, so you can grab it right from there. That's omega. And what's the value of L? L is given to be 40 microhenry, right? So 40 microhenry. Okay, so once I do that, I'm going to end up with the ZL equals to J 8 ohms. Okay, so this is the first step. Let me see if I can highlight this guy. Okay, so the first step I did was to express the current in a phasor form. The next step I did is to translate, okay, the inductor to frequency domain. Okay, let's do the exact same thing with the capacitor. There's a capacitance C over here, right? Let's translate the capacitance in frequency domain, which can be expressed as ZC when you translate in frequency domain, which is 1 over J omega C. 1 over J omega C is the same as negative J over omega C, because I can write this 1 as negative J squared, right? Negative J squared is 1. J squared is negative 1. Negative J squared is 1. So all I have done is to bring this J to the numerator. Okay, so that's the idea behind translating the capacitance into a frequency domain, negative J over omega C. So which is going to be negative J over omega is 2 into 10 to the 5 into C. What's the value of capacitance given to be? The value of capacitance is given to be 1 microfarad. So I'm going to plug that capacitance in here. 1 microfarad. Okay, 1 microfarad. Okay, once I do that, I'm going to get a value of ZC equals to negative J 5 ohms. Notice that all of these impedances, Z, L, ZC, and R, are in the form of ohms. Okay, now what I have simply done is to start with the phasor representation of the current and then translate inductor into frequency domain and capacitance into the frequency domain. Now I'm ready to convert this circuit into the frequency domain. So I'm going to take this, copy this guy, okay, paste it over here. Okay, let's start with this guy in frequency domain. So here the first question was to translate this into frequency domain. So this 1 microfarad capacitance is going to come out to be negative J5 ohms. Okay, the resistance of 6 ohms is going to be still the same. Then this 40 microhenry inductance is translated into the J8 ohms here. Okay, so this guy is J8 ohms. Okay, the 10 ohms resistance is still going to be the same. Remember, the resistor is still the same in frequency domain and time domain. Now let me see if I can convert this current source, IS. Okay, this IS is 8 amperes, 8 angle 0 amperes. Remember, the first thing I did was to translate the current source into 8 angle 0. So I have completely solved the first part. Okay, the first part of the circuit of the question was to find the frequency domain equivalent. Here it is. The frequency domain equivalent is this guy. Okay, the impedance expressed as complex impedance for the inductor and the capacitance. Everything else is the same. Questions so far, please. Okay, so let's see if we can move on to the next part of the problem. Okay, part number 2 of the problem is, let's see, what color did I use up there? Part 1. Part 2 of the problem is, find the value of I1, find the value of I2, and find the value of I3. Okay, and of course the V, the voltage across the sky. If I call this as capital V in the phasor form, what's little v? If I go back to my circuit here, so if this guy is little v, the time domain expression, the steady state time domain expression for V is what? That's the second part of the circuit. Okay, so let me see if I can translate all of these into capitals as well in the phasor form. Okay, I2, and of course I3. Okay, so the second part is to find the, let me write it out, find the steady state expression for the above. Okay, I know writing it out all in words is time consuming, but I still want to, there is some value that we can get by spending the time that we spend, taking it deliberately, slowly, in a very slow pace. Okay, that way we know exactly what we are doing. Okay, so the method I'm going to follow here in order to find little I, little I2, and little I3 is to first find capital I1, capital I2, and capital I3, and capital V. Once I find these, okay, then I can translate from phasor to time domain. I'll give you an example. Let's say I3 just picking a random number here, came out to be 5 angle 25. Okay, then I know how to write it in the time domain. I'm simply going to write it as 5 cosine omega t plus angle 25. So I know once I have the phasor, I know how to go to the time domain form. Okay, that's exactly what I'm going to do. I'm going to begin by finding the phasor values for I1, I2, and I3. Okay, questions, please. Questions so far. Okay, so let's see. Let's try to find the value here. So I know for a fact that here, find the value of I1, I2, I3, and V, which is right here, the voltage across these two terminals. Okay, now if I have to find the voltage across these two terminals, if I want to find the voltage across those two terminals, right? These terminals, these are all in parallel. So if I find the voltage across these terminals, that's going to be the same through all the three branches. There are three branches, right? See, 1, 2, and 3. There are three parallel branches here. So if I find the overall current, I know the overall current, 8 angle 0 degrees, okay, and find the overall resistance or Z equivalent of all the three parallel branches, then I would get V. Okay, in order to do that, let me see if I can find the overall equivalent of three resistors, okay, of three branches. There are three branches here. So I have the first branch where there is a resistance of 10 ohms. Okay, the resistance of that 10 ohms is 10. And I'm going to find the reciprocal of that is 1 over 10 ohms. Because they're in parallel, it's convenient for me to find out the reciprocal of all of these numbers so I can add them in parallel. Okay, what's the next branch? Now, if you look at the second branch, which is, oops, so let me clear all of this and show some color coding here, careful color coding. So this guy, this resistance here is shown right there. Okay, now I'm looking at the next branch, which is this guy. Okay, in this branch, what is the overall impedance in branch 2, which is the impedance of the inductor and resistance in series. So that's going to be 6 ohms for the resistance on top plus J 8 ohms. Okay, that's the impedance, the overall impedance of this guy, of this branch. Okay, now if you pay attention, I'm simply solving this circuit as if all the components are simple resistors, except with a complex number. So now I'm going to find the admittance of this guy, or the inverse of this guy, as 1 over 6 ohms plus J 8 ohms. Okay, because it's convenient for me to find the inverse when I'm dealing with parallel impedances. Okay, similarly, let's look at the third branch. The third branch, let me show it in this color. Okay, I'm going to show you the third branch in the blue color, sky blue color. Okay, let's see. The third branch has an impedance of a capacitance, okay, which is simply negative J 5 ohms. Now, if I find the reciprocal of that, which is called the admittance, it's going to be negative J5 in the denominator. Everybody with me so far? Questions, please. Questions so far, please.
Looks good.
I have no questions. I'm just trying to follow along.
Okay, good, good, good. Let's see. So here is the circuit, okay? And I found out that each of these branches has some resistance and impedance. YR, the 1 over resistance for the first branch is 1 over 10 ohms. That's this guy, okay? Then the impedance is for the blue branch, this ZC. And then of course, this guy corresponds to the green branch, okay? So corresponding to that, I'm calculating the inverse here, the admittance component there, just so it's easy for me to add in parallel. Okay, so if I am to find the overall impedance here of the three parallel branches, Z equivalent is equals to 1 over R plus 1 over ZL plus 1 over ZC, okay, which is this branch is shown in all of that inverse. See, three parallel resistances, the equivalent R equivalent is equals to 1 over R1 plus 1 over R2 plus 1 over R3, the whole inverse, right? Or in other words, 1 over R equivalent of three resistances in parallel is the sum of reciprocals. That's exactly the theory I'm using here. In frequency domain, when you account for complex J frequencies, you can simply treat these impedances as complex resistors. Okay, so there are three branches. Corresponding to those three parallel branches, I have three impedances. Now, fortunately, I have already calculated the values for these, or at least started calculating the values for these guys. Okay, 1 over R. Okay, 1 over R, which is shown as is 0.1 ohms or 1 mho Siemens. Okay, that's the unit for 1 over ohms. Okay, this is the exact opposite phenomenon of resistance. Similarly, so that's the 1 over R, the one highlighted in purple. Its value is right here. Okay, that's the value of 1 over R. Similarly, the value of 1 over ZL is exactly 1 over 6 plus J8 omega, which is going to be 6 minus J8 omega by 100, 6 squared. So all I have done is to multiply the numerator and the denominator by the complex conjugate, okay, which is 6 minus j omega. So all I have done is multiply the numerator and the denominator of both of these terms by their complex conjugate. 6 plus j8 multiplied by 6 minus j8. Its value does not change if I multiply both the numerator and denominator by the same term, 6 minus j8. Okay, once I do that, I'm going to be left with 36 plus 64 in the denominator. Okay, or in other words, it's going to come out to be 0.06 minus j 0.08 for this guy. Okay, for the second branch. Okay, and then let's look at the third branch, which is 1 over j5 omega, which is going to come out to be j 0.2 mho. So all of this is in mho or Siemens. Okay, all of this is in mho. So this guy is the inverse of ohms. So it is shown as MHO. It's ohms written backwards. It also has the units of Siemens. Okay, so now I have all the three terms. Okay, if you look at this equation here, okay, if you look at this equation here, Z EQ equation, I wanted the purple, I wanted the green, and I wanted the blue, and here I have them. The purple is 0.1, the green is this guy, and the blue is 0.2 j omega 2. Now I should be able to find Z equivalent. Okay, let's see. Z equivalent, therefore, is the sum of the purple, the blue, and so on and so forth, all the waves, which is going to come out to be, let's see, YR plus YL plus R plus YC, which is going to come out to be 0.16 plus J 0.12 mho. Okay, it's simply the addition of the purple, green, and so it's this guy, blue. Okay, the purple and the green components. Okay, this is what I would get. Z equivalent is 1 over that guy. I'm sorry, this is the Y equivalent. So if you want to find the Z equivalent, it's going to be 1 over Y equivalent. So if you remember, 1 over R equivalent of 3 resistors in parallel was 1 over R1 plus 1 over R2 plus 1 over R3. So if you wanted R equivalent, you had to do the inverse of that. Okay, so that's exactly what I'm doing here. Very simple business. 1 over all of this. So 1 over all of this is going to give me the Z equivalent. So let's see. Now 0.16 plus J 0.12 mho is in the rectangular form, right? It's in the rectangular form. And I want to convert it to polar form. Okay, just so it's convenient for me. When I want to go from rectangular form to polar form, I'm going from x plus jy form to a to the angle phi form. Okay, here a is going to be square root of x squared plus y squared, which is going to be 0.16 whole squared plus 0.12 the whole squared. Okay, so this is all the y equivalent in its, this is all of this is y equivalent in its rectangular form, and I'm converting it to polar form, and you'll see why I'm doing that in just 1 second. Okay, now so therefore a is going to be square root of 0.16 squared plus 0.12 squared, and then angle is going to be, this angle is going to be, anybody remember the expression I gave for angle? Let's go back. Okay, let's go back and see what I have written. When you're going from rectangular form to polar form, okay, the magnitude is given by the sum of the squares, and the angle is given by what? Tan inverse of y over x, tan inverse of imaginary part over the real part. So let me go there. So it's going to be tan inverse of imaginary part over the real part. Okay, in here, the imaginary part is 0.12. So tan inverse 0.12 over the real part, which is this guy. Okay, 0.16. So that's 0.16. So now, once I do this, I get an expression for A, I get a value for A, and I get a value for phi. So 0.16 plus J 0.12 mho, which is the Y equivalent, is expressed as 8 angle phi to be 0.2 angle 36.87 degrees. Okay, so this is phi, and this is A. So this guy comes out to be 0.2 when you do this math here, and this guy comes out to be 36.87. Okay, when you do this math here. Okay, now if you think about it, Y equivalent is 0.2 angle 36.87 degrees. Now I'm going to find a Z equivalent, which is the inverse of Y equivalent, which is 1 over Y equivalent. 1 over Y equivalent is simply, so there is an angle component, there is a magnitude component, 1 over 0.2 would be the magnitude of the inverse. The angle is going to be negative 36.87 degrees. Okay, so when you take a number and try to find the inverse of it in the polar form, it's very easy to do. Okay, you simply divide 1 by that magnitude to get the magnitude, and you put a negative sign to get the angle. Okay, and that's the exact reason why you're going from the rectangular form to the polar form. because it's easy to do division in rectangular, in polar form. Okay, let's see, let me add a page. Okay, so here I am, Z equivalent with a value of 5, which is 1 over 0.2, angle negative 36.87 degrees. Does that make sense at all? And all of this is in ohms.
Yes.
So all I have done is to find Y equivalent in the rectangular form as a complex number. Okay, then I translated Y equivalent to polar form. Then I found 1 over Y equivalent to be Z equivalent. Once I have a Z equivalent, I should be able to find V. Okay, V is Z equivalent times I. So let me go back. Let me go back really quickly. Okay, so here I'm going to copy this guy. Okay, I'm going to go back here, add a page. Okay, now if you think about it, what I have done so far, and I'm taking it at a very, very deliberate pace. Okay, what I have done so far is to replace, okay, is to replace all of this, okay, all of this with its Z equivalent. Okay, all I have done is to represent this guy with its Z equivalent. Z equivalent. So in order to find the Z equivalent, what I had to do was to do the parallel simplification. Once I have Z equivalent, and its value is 5 angle negative 36.87, right? 5 angle negative 36.87. Okay, once I have the Z equivalent, and once I have the current, I would be able to find out V. V is Z times I. Okay, and that's the whole reason why I did all the conversions I did. I did parallel simplifications, so on and so forth. Okay, so let's find out why. V, I'm sorry. Let's find out V. V is Z equivalent, which is 5 angle negative 36.87 degrees. That is Z equivalent times I, which is 8 angle 0 degrees. Everybody with me so far? This is I. This is Z equivalent. Okay, this is Z equivalent, and notice that both of these are in the polar form. Okay, multiplication is absolutely easy. Multiplication is easy in polar form. Okay, so when you have product, when you know you have to find some product, you convert all your numbers into polar form. Okay, in multiplication, all you have to do is to multiply this number with this number, which is 40. And when you have angles, you simply add them. Does that make sense? So the voltage here, that's one of the things we wanted to find out, is 40 angle negative 36.87 degrees. Okay, does that make sense? Questions, please. Let's try to, can we express this voltage in the time domain? How would you express this in the time domain? So what I have here is Vm, and I have an angle of phase phi over here. Okay, so if I want to express it in the time domain, it's going to be Vm cosine omega t plus phi, where Vm is 40 cosine. Omega t was given to be 2 into 10 to the 5. Omega was given to be 2 into 10 to the 5t, plus phi is negative 36.87 degrees. And all of this is in volts. Questions, please. Questions so far. Okay, let me go back. Let me go back and carefully review, retrace the steps that I have done so far. Okay, so the question was to, if you think about it, part 2, the question is find the steady state expression for V. Okay, for V, I1, I2, and I3. Okay, so if I'm given, so let me give you a circuit here. If I'm given 3 resistors in parallel, okay, how would you go about finding the voltage here? Well, you'd simply find the equivalent resistance, 1 over R1 plus 1 over R2 plus 1 over R3. That's the overall equivalent resistance. Okay, then you multiply that resistance with the current, so you get a value for V. That's exactly what I have done here. Okay, all I have done is to look at these 3 branches in parallel. I found the equivalent resistance, and once I found the equivalent resistance, I multiplied that equivalent resistance with the current to get a value for V. Okay, and along the way, I had to convert from time domain to rectangular form to polar form, and interconvert between all of those. Okay, so if you notice, I started off in the rectangular form, 6 and complex number J8. Okay, then I eventually translated this sum. Okay, if you think about it, I have done the sum in the complex domain. Okay, I simply added the real part and imaginary part, and I did the product. Okay, and I did the product in the polar form. Okay, I'll say this one more time. Let me write it out clearly here. Okay, when you're doing multiple conversions in time domain, rectangular, and polar form, they're all equivalent. You could do the exact problem, all of it in the rectangular form, in a complex number domain completely, and still get the answer. You could do the whole problem in polar form and still get the exact answer. But it's much easier to do add and subtract in the polar form, in the rectangular form. It's much easier to divide and multiply in the polar form. Okay, I'll give you an example now. Okay, let's retrace. So this is our solution here, right? So the V value, the voltage was found to be, so in other words, if I were to paste this guy here, okay, let's see, the voltage in this parallel circuit, okay, the voltage along this parallel circuit. So here is a question coming at you. So I gave you the value for this voltage, right? The voltage V was given to be 40 angle negative 36.87 degree volts. How can you find the value of I1, the value of I2, and the value of I3? If I give you the voltage across 2 terminals of a device, how can you find the current?
The current for the resistor is the voltage divided by 10 ohms.
Voltage divided by the resistance. Correct. How about I2, the current flowing in this branch? That would be the voltage, that's still the same, divided by the Z of L plus R, right? The voltage divided by the impedance, which is simply, if you think about it, okay, let me draw a partition here. Now, V times 1 over Z L plus R is YL plus R. Okay, YL plus R. Remember, we calculated, we did that math already. We calculated this value, YL plus R. We found its value, right? So that's what we are going to stick to. Okay, so let's see. You're right that when you want to find the current I1, you simply take V and divide it by R. Okay, so let's see. V is 40, angle negative 36.87 degrees, divided by R is 10 ohms. So I1 is going to come out to be 4 angle negative 36.87 degree amperes. Okay, this is I1. So look what I'm going to do here. I'm going to convert this I1 into little I1 as a time domain expression, which is going to be 4 cosine omega t. Omega was given to be 10 to the 5 t plus angle phi. Angle is 36.87 degrees amperes. So this guy is one of the problems that we were asked to find out in part 2. Remember the time domain steady state expression for I1, I2, I3, and V. Okay, fortunately, we found the answer to time domain expression for V. Okay, questions, please. Questions so far. Okay, so the next part is to find I2, which is the current flowing in this branch. Okay, the current flowing in that branch. The current flowing in that branch is this guy. Okay, the current flowing in this parallel branch is V over the voltage Z, or the impedance of this guy L plus R. Okay, see what I'm going to do here. I'm going to leave this voltage in its polar form, 40 angle negative 36.87 degrees. And what was the impedance ZL? Let me go back to this guy. ZL was 6 plus J8 ohms. Remember, Z equivalent was 6 plus J8 ohms. So this is what I'm going to do. I'm going to write it. Okay, I2 is the voltage across this guy divided by 6 plus J8 ohms. Okay, this is what I'm going to write for the current here. 6 plus J8 ohms. Okay, now what I want to do is to do the division in polar form. Okay, so I'm going to write I2 to be 40 angle negative 36.87 degrees divided by, what is the polar equivalent of this guy? 6 squared plus 8 squared under root angle tan inverse imaginary part over the real part. Okay, so which is going to be 40 angle negative 36.87 degrees divided by square root of 6 squared plus 8 squared is 10. Tan inverse 8 over 6 is going to come out to be 53.13 degrees. Okay, now it's easy to solve this division in polar form. You simply divide 40 by 10, which is going to be 4. And when it comes to angles, all you have to do is negative 36.87 minus 53.13 degrees. Okay, so it's going to come out to be I2 is going to come out to be 4 angle negative 90 degrees amperes. So if you were to write it in the time domain form, I2 of t, okay, that's going to be, so I2 of t is going to be, okay, 4, that's this guy, cosine omega t plus angle phi, which is 90 degrees amperes. Okay, so this is the other part of the problem that we wanted to find, I2. Dang it. There you go. Okay, so let's try to find the other current as well, I3. Let's find I3. Okay, let me see if I can add that image back here. Okay, forget about the rest of these circuits, I1, I2, because we already found them. Okay, okay. Now, in order to find I3, what I have to do is to divide the voltage across that by this impedance, negative J5 ohms. That's exactly what I did here. In order to find I2, I had to divide voltage by 6 plus J8 ohms. So this is what I'm going to do here as well. Okay, for this branch, for the third branch. Okay, now let's see if I can divide voltage V, which we found out to be 40 angle negative 36.87 degrees. Remember, that was the first result that we got. That's this guy. Okay, so 40 angle negative 36.87, that's the voltage across the capacitance, divided by the impedance of the capacitance, which is negative J5 ohms. Okay, and like I mentioned, you want to do the division in the polar form, divide in the polar form. Did I write divide in polar form? Okay, so I3 is going to be 40 angle negative 36.87 degrees divided by the polar representation of negative J5 ohms. Okay, that is square root of real part squared plus imaginary part squared, and the angle tan inverse of real part over imaginary part. Is everybody with me so far?
Yes.
So I3 is going to come out to be 40 angle negative 36.87 degrees divided by, this is going to come out to be 5, and this is going to come out to be negative 90 degrees. Okay, now I3, it's easy to do the division in the polar form. You simply have to divide these two, and then when it comes to angles, you subtract them. So I3 is going to be 8 angle 53.13 degrees amperes. Now, if you want to write it in the time domain form, I3 of t is 8 cosine omega t plus phi where omega is given. We know omega, right? 2 into 10 to the 5 radians, okay, times t, plus the angle is 53.13 degrees. Okay, that's the third part of the problem we wanted to find. Questions, please. Questions so far. Okay, so let me quickly summarize the big picture of what we have done here. Okay, we started with some time domain. And in general, this is what we would do. If you have a time domain expression, cosine omega t plus phi, okay, and you want to convert it to polar form or a phasor representation of this guy, you simply take the Vm and the angle. When you want to go from this part to the complex number form, all you have to do is x is Vm cos phi, y is Vm sine phi. Okay, but if you want to go backwards, you would simply have to write Vm equals to x squared plus y squared, real part squared plus imaginary part squared. Phi would be tan inverse imaginary part over real part. Okay, we'll look at some examples to see if we can convert back and forth between these two. Okay, questions, please. Questions so far. Okay, so let's look at one more example. We have about 15 minutes of time. Example 2. Okay, conversion from time domain to phasor form. Okay, I give you a time domain expression. V is 170 cosine 377t minus 40 degrees. And what is the phasor equivalent of it? What's the phasor form of it? That's what we are expected to find out. So this problem is an easy problem. The phasor equivalent of this is simply 170 angle negative 40 degrees. Okay, let's look at another example. Let's do some quick examples here. B, okay, current is given to be 10 sine 10,000 t plus 20 degrees. And we are expected to find the phasor form of this. Okay, in order to find the phasor form, all I'm going to do is I'm going to write this guy. I is 10 sine 10k plus 20 degrees minus 90 degrees as a cosine. Okay, sine of theta is cosine of theta minus 90 degrees or 90 minus theta. Okay, sine of theta is cosine of theta minus 90 degrees is the trigonometric identity I am using here. Okay, because I want to express everything in my standard cosine form. Now what I have is I can represent this guy in the phasor form as 10 angle negative 70 degrees. Okay, that's the quick conversion from time domain to phasor form. Okay, so we're trying to get as many example problems as we can. Now let's do another example problem here. This is a little bit more interesting problem. It's a bit more involved. 5 cosine omega t plus 36.87 degrees plus 10 cosine omega t minus 53.13 degrees. And we want to convert this to phasor form. Okay, how do you convert this to phasor form? Okay, let's see. What is the operation that I'm interested in here? Addition operation, right? So here is the strategy I'm going to do. Okay, the strategy I'm going to follow is to express this. So it's clear that I cannot add two trigonometric terms directly. Okay, I cannot simply add these two trigonometric identities. So what I'm going to do is to convert this to polar form A1, phi 1, plus convert this to polar form as well, A2, phi 2. Can I do that addition easily in polar form? No, I cannot. Remember, let me go back. If I go back, I must have mentioned somewhere in here.
It's in rectangular form. You need to add, yeah, or subtract.
Correct. In rectangular form, I want to add and subtract. In polar form, it's easier to multiply and divide. Okay, that's the observation. That's the insight I'm going to use in order to solve this. So I cannot add directly in the polar form. So I want to convert this to rectangular form, x1 plus j y1 plus x2 plus j y2. Now I can add these two numbers, x1 plus x2 plus j y1 plus y2. Now I can convert this back to polar form. So I'm going to have to jump back and forth between time domain to polar, polar to rectangular, rectangular back to polar. Okay, interesting. Let's see if we can convert the one on the left, 5. What's the polar equivalent of this guy? 5.
That is 5 degree 38.87 degrees.
38.87. So let's see, it's 36. I should have written it clearly. Okay, so let's see, 36.87 degrees plus, what's the polar equivalent of this guy?
10 negative 53.13 degrees.
Thank you. So this is the phasor equivalent. So let's quickly convert them to rectangular form. Rectangular form is going to be 5 cosine of 36.87 plus j sine of 36.87 degrees. Okay, that's the one on the left, plus the one on the right is 10 cosine negative 53.13 degrees plus j 10 sine negative 53.13 degrees. Okay, so let's see. So this is going to come out to be this guy is going to come out, oops. This guy is going to come out to be 4 plus j3 plus this guy is going to come out to be 6 minus j8. Everybody with me so far?
Yes.
So now it's easy to do the addition in rectangular form. I simply add the real part. There's a real part of 4 and there's a real part of 6. So I simply add them to be 10. And then when it comes to the imaginary part, I'm simply going to add those corresponding terms, which is going to come out to be negative j5. Okay, once I have the rectangular form, so this represents the rectangular form of the sum for these time domain cosine waves. Okay, there's absolutely no way I can easily add the terms in the cosine form. Okay, I cannot add them in the polar form. So I came into the rectangular form where it's much easier to do the math. Now I can go back to polar form. Okay, let me go back to the polar form. So when I am to convert into the polar form, the magnitude is going to be 10 squared plus negative 5 squared angle tan inverse of imaginary part over the real part. Does that make sense? So square root of 10 squared plus negative 5 squared is going to be 11.18. Angle tan inverse of negative 1/2 is negative 26.56 degrees. Okay, does that make sense? So the idea was the question was to represent all of this in the phasor form, right? So we cannot simply add them in time domain. We cannot add them in the phasor form. So we had to convert them individually into phasors, then into rectangular form, then add them in the rectangular form. From there, get the phasor equivalent. There is your answer. Questions, please. Questions so far. Okay, so I kind of summarized the steps that we have to follow right here. Okay, when you want to go from a rectangular form to polar form, what you'd have to do is square root of x squared plus y squared under root, and tan inverse imaginary part over real part gives you the angle. If you want to go from the phasor to rectangular form, you'd simply have to do Vm cos phi, Vm sin phi. Okay, so there's no shortcut to this. You just have to have this in your head and be comfortable, absolutely comfortable going from one form to another form. Okay, questions, please. Questions so far. What questions do you have at this time? Okay, let me pause the recording here for a second.